third is machines, fourth is materials, and fifth is moment. So these five components has to be managed properly for a successful venture. And of course, the role of GIS in supply chain management is responsible for managing moment, managing materials, and managing machines. And up to some extent, it is also responsible for managing the manpower. The second advantage that GIS enjoys in supply chain management is like it is a big single database platform for storing logistics data that can be analyzed at a greater convenience, or I should say at ease. And it has enabled tracking and movement of goods and service from the manufacturer to the market with the advent of GPS and global navigation based satellite system technologies. So these things have been quite possible. One of the examples in is like the truck dispatch system in the mining industry, or the vehicle based GPS service that is being extensively used in cab services like Ola and Uber services. Then the fourth advantage that GIS enjoys is it prevents the consequences of accidents, delays, and undesirable circumstances. So this factor minimizes the the cost of time, and that helps to optimize or maximize the performance of the supply chain management. And finally, GIS enhances profitability for both the manufacturer and the market. If the manufacturer saves time in delivering the goods and services, and if the customer receives the same at a shorter period of time, so both are in a profitable situation. So we would be mostly discussing the role of GIS on the transportation aspect of the supply chain management system. And one of the key aspect in transportation is the emphasis on route optimization. Route optimization includes these five aspects: minimizing the route distance, or in terms of the path length, minimizing the travel time, optimizing the resource allocation, assigning paths, and maximizing the good supply, or say maximizing production. So when we discuss regarding the route optimization techniques, so there is some cost function that is associated with these sort of optimization techniques. Like most of the uh, there have been some algorithms like the Bellman-Ford algorithm, Prim's algorithm, and Dijkstra's algorithm that are extensively used for route optimization. And these algorithms are mostly covered in graphical analysis or graph networks in computer sciences. So like we can just have a quick overview of Bellman-Ford algorithm. So like Bellman-Ford algorithm is mostly used for directed graph when it has both positive as well as the negative weights. And in each iteration, the weight values gets updated when we traverse from one node to the another and search for the best possible route that minimizes the weights with respect to the previous node that was traversed. And the second algorithm is the Dijkstra's algorithm. In the Dijkstra's algorithm, when we have a source of nodes in the network or the source of vertices, in this case, it provides an overview of the network information that is like that is analyzed in order to find the in order to find the least cost path that is possible between two nodes or set of nodes. So this is the algorithm of the Dijkstra's optimization technique. So the differences in two algorithms is that Bellman-Ford algorithm works for negative weightage, while Distrust's algorithm does not work for the same. Bellman-Ford's algorithm contains information about individual connected vertices, like in each iteration, uh, just by looking upon the previously traversed node, it updates the weight value for each of the new vertex, while the distrust algorithm, it contains the information about the whole network. Bellman-Ford's algorithm can be implemented for multiple points simultaneously, while this cannot be implemented for the distrust algorithm. Then the fourth point is that Bellman-Ford's algorithm, since it takes into account all the vertices for updating the weights, so the computational complexity increases, while the distrust algorithm, the computational complexity is less. Dynamic programming approach is involved in Bellman-Ford's algorithm, while greedy programming approach is involved in distrust algorithm. For Bellman-Ford's algorithm, iterations are performed over a number of edges for each vertices combinations. While for the distrust algorithm, it minimizes the distance from the source node and iterations are performed over vertex extractions. So now, like when we move into the use of QGIS for route optimization, we mostly focus on finding the shortest path. The shortest path can be expressed in terms of the distance or in terms of the time. Like when it is expressed in terms of the distance, so we say it as the minimum distance path, or when it is expressed in terms of the time, we say it as the fastest path. Uh, Most of the GIS software have inbuilt route optimization toolbox. Mostly, they have the network analysis toolbox. We would be dealing with the QGIS software for practical session, and it has a processing toolbox of network analysis, which is a part of the vector toolbar that is used for route optimization in transport and logistics. It works on the lines of distrust algorithm and calculates the shortest path between 2 points on any polyline layer and plots this path over the road network. The salient features of the network analysis that is used in QGIS is it calculates path as well as the cost, either expressed in terms of the length or time. Secondly, it optimizes by length of travel time and exports the path to a vector layer that can be used for further analysis. The advantage of using QGIS for route optimization is that it can be integrated with further programming like resource allocation or even path assignments and obtaining the service area for any particular source destination based problem. So for our analysis today, we would be using the QGIS software for route optimization. So let me just open the software. So the first exercise that I'll be implementing is finding the shortest distance or the minimum distance path between any 2 points for a vector layer. Is anyone using the QGIS software for today's practical session? Okay. So here we have, three layers. One is the polygon layer that shows each of the polygon features. This is a map of IIT campus that's in Mumbai. So this first feature is the polygon layer, featuring some of the aspects of the campus. The second feature is the line feature, describing the routes. Routes are the roadways. And these features have been laid on the OpenStreetMap database in order to look for proper geo-registration. So the first thing that I'll be doing is finding the finding the minimum distance between 2 points. Suppose if I want to find the distance between like main gate to say KV ground, Kendra Vidyalaya ground. So how to do this is to go for the network analysis tools, select the option shortest path point to point. So here it opens a toolbox. In the toolbox parameters, you have to give input for each of the options. The first is the vector layer representing the network. So in our case, the IIT lines is the vector layer that represents the road network. The second field is path type to calculate. Here there are two options, either going for the shortest or going for the fastest. So if we are considering for the minimum distance case, so we will be going for the shortest path. The third field it is asking is for the start point. So for the start point, we need to select the point, the corresponding point in the map. So we just click on this option and it gives the cursor. So in the cursor, we click on, say, the main gate road. We click at this point. So it automatically extracts the coordinates from the geo-registered lines and feeds it into this field. So similarly, we will be going for selecting the endpoints. For going for the endpoints, so the destination that we had selected is the KV ground. So let us select here. So it also, the coordinates got automatically fed here. And further, we can go for the field of advanced parameters. Here we don't have any direction field since it is a simple vector layer consisting of the line-based shapefile. So directions are there only if there would have been cases of one-way entry or multiple ways entry and exit. In these cases, there would have been a separate field of direction. So in these cases, there is other options of value for forward direction and value for backward direction, or value for both directions. So we have the default direction as both directions, like vehicles or pedestrians can go in both the ways. There is another field of speed field. In this case, since we are only interested to find the minimum distance, so we don't have to select anything on the speed field. We just leave it as blank. And the default speed, let us say we can assign any value, whether it is 50 kilometer per hour or 25 kilometer per hour. And for topology tolerance, like we don't have the values in the attribute table, so we just leave as it is. So we create a temporary layer of finding the minimum distance. So we click on, so here it gives the log that the shortest path point to point is finished. So when we see the shortest path that has been generated, in order to highlight the shortest path, let me change the line type. So we go for the option of symbology. Let us say we select the black color option and give a width of say 1. And then we click on apply. So here the black colored line, this represents the minimum path from the main gate to the Kendra Vidyalaya via the shapefile, via the road shapefile. If we want to measure the distance of this path, so we open the attribute table, we right click on the shortest path, open the attribute table, and look for the attribute of cost. So here in the cost, we find a value of 0.0056. So this cost is expressed in kilometers. So if we want to convert it in meters, so we simply uh, no, this cost function has been expressed in terms of, yes, kilometers. So we can simply add 1000 to get the cost function in meters. And this route, the black colored route, this represents the shortest distance from the main gate to the KV ground. So let us take another example. Like if we want to see further distance from, say, somewhere inside the IIT campus to another location, say the nearest railway station. The nearest railway station is located in Kanjurmarg. So if you want to find the minimum distance, so in this case, we will be doing the same thing. We will be going for shortest path point to point. the vector layer that is representing in the network IIT lines, path type to calculate the shortest, start point, let us say we can start from somewhere along the laboratory street, and the end point we can go up to the Kanjurmarg West railway station, which is at this point. So here at advanced parameters, we don't have to mention anything. Default speed, let us say here at 50 kilometers per hour, and then we select run. Okay, let me again try. Okay, let us select the start point somewhere at this junction. End point somewhere along this junction. Let us keep the advanced parameter as it is, and then click on run. Okay. So here, when we again view the shortest path, so here we can see this is the route that provides the shortest path from some point inside the campus to the nearest railway station. So here we are only considering the shortest path in terms of the minimum distance. We have not taken into consideration the effects of, say, road traffic, or even the effects of curvatures or other topological effect if there is a road inclination or the condition of road. We are not taking into consideration any of the things. We have only selected here the minimum distance possible via the road in order to reach from a point inside the campus to the nearest railway station. So moving on to the next aspect. So let us further select some point farther away and then use the shortest path. But before that, uh, if I just hide the OSM map, and if we can observe the route map, the line feature corresponding to the routes. So here we can see this is the vector layer, or this is the shapefile that shows the routes within a particular place. And we have the OpenStreetMap as a whole. So in this case, if we use the shortest distance to find the route from any point inside the campus to, say, airport. So let us give it a try. So again, we do the same shortest path, vector layer representing the network IIT lines, path type to calculate shortest, start point is somewhere we can select from, say, a bit farther point, say from this junction, and end point. we go for the airport at this point. Let us keep the advanced parameters as it is, since we are only interested in finding the minimum distance. So now let us click the run button. So what message it is showing? That there is no route from the start point to the end point. So can anyone give the reason why it is so? Why it is showing that there is no route from the start point to the end point? Hello, am I audible?
Yes, sir.
Audible.
Okay. So any answer? Why it is showing this message that there is no route from the start point to the end point?
I hope there is no road connectivity between them.
Like the OpenStreetMap, it is showing that there are roads. Like if you see the OpenStreetMap, you can see, for example, if I go by this way, like here is the campus, and you can go from here in this route and again come to this route JVLR, and again you can go by this road to Sakinaka and then reach the airport. The OpenStreetMap is showing this, but why the shortest path said that there is no route? The answer is simple.
This route is one-way roads.
No, it's not a one-way road. Okay, let me tell the answer.
During
So,
the flight,
sorry,
flight route.
flight route? No, no, no. Like we want to go from the campus to the airport via road. The OSM map is showing that there is a road. Like you can go from this way to Powai, and then you can take a left turn from the JVLR and then go to Sakinaka and take the approaching road to the airport. But our shortest path said that there is no route from the start point to the end point. So the reason is the shortest path is working on which layer? Is it working on IIT lines layer or the OSM standard layer? The shortest path is working on the IIT lines layer. IIT lines layer is a vector layer. It is a shape file. While the OSM standard, it is a map file. So like just before starting this exercise, I had shown this feature that if I hide the OSM standard, so here the vector layer is limited up to some extent. The vector layer has no further features to the airport. Like if we see the airport is somewhere along this region, and the vector layer ends at the Powai area. So if there is no vector layer that is available to the airport, so the shortest path algorithm would be unable to identify the shortest route from the point inside the campus, which is the start point, to the end point. The end point was assigned as the airport. So since it does not have any vector layer within the files of IIT lines, within the shape file of IIT lines that correspond to a route from the IIT campus to the airport. So here in this case, the shortest path toolbox will be unable to find the shortest route from the point to the airport. So I hope this like concept is clear. Okay. So we can move on to the next aspect. If you want to use the OpenStreetMap and the vector layer, if you want to use the vector layer for finding the shortest distance between a group of points to the destination point. For example, let us think about a scenario that a person has come new to Mumbai and he would be joining, say, the campus, the IT campus for a job, and he's searching for apartments nearby, residential apartments where he wants to stay. So, so he would look for somewhere which is quite near to his workplace. So let us say he goes to the Powai region, near to the Powai lake. He starts searching for some of the apartments, some of the residential apartments. He selected these 6 points, and he wants to make a decision as which apartment he wants to choose that would minimize the distance from his staying place to his workplace. So in that case, how QGIS will be used for calculating the shortest path? So let us put back the OSM standard map. This region represents mostly the residential areas. So let us say we add some points here. In order to add points, just click on this new shapefile layer. Let us give a file name as residential Hawaii. Here the geometry type, since it is a point layer, so we will be going for point. And let us keep the reference system as World WGS 84, World Geodetic Survey 84 system. And we simply click on OK. So in order to add points, we select this layer, residential Powai. We click on this option of toggle editing in the vector toolbar. And again, we select add point feature. So here we see the cursor got changed. So we can just add some points, for example, near Glen Heights. Let us just give a ID, say 1. Another at Heritage. Let us say ID 2. Octavius, ID 3. Somewhere at Empress Hill, ID 4. Regent Hill, ID 5. Castle Rock, ID 6. And let us say one more residential place. We can select for Spectra, which is ID 7. So these points represent the source points. That means the points corresponding to the residential apartments. Now again, we have to select another point, which is the destination point. The destination point will be the workspace inside the IIT campus. So here what we will be doing, we will be saving this layer file, residential Powai. So we just click on here, save layer edits, and unselect this toggle editing option and add,
After that,
yes, sorry. Okay. So instead of adding another point to this residential power area, we have to look for the options in the network analysis. There is the option of shortest path layer to point, then shortest path point to layer, and shortest path point to point. So this feature residential power is a layer. It is a point feature layer. So here we have to go for the option of shortest path layer to point, where the source points will be represented as a feature layer vector and the destination point would be a single point. So here if we go for this option, shortest path layer to point, so as usual, the first field it is asking vector layer that is representing the network. So we will go for IIT lines. Path to calculate, we'll go for the shortest. Vector layer with start points. The start points is where the residential apartments are present. So it will be the feature layer of residential Powai. And for endpoints, we have to just click on this button and we have to select somewhere inside the campus. Say CSRE library. And advanced parameters, we keep it as it is. We have the default direction of both directions and say default speed of 50 kilometers per hour. And we create a temporary layer and select the run button. Okay, so it has the output that shortest path between layer to point is finished. So if we now visualize the shortest path from layer to point, we select here. We change its color, give some width. Okay, I think the software got a bit stuck. Okay, I think the software just got a bit stuck. Okay. So again, let me just repeat the same thing. Just a second. So here we go for the network analysis. The shortest path layer to point. IIT line, shortest vector layer with start points. Okay, we need to create a point layer. So we put the file name residential Powai, type point, select OK. I think we already have this. Okay. We go for edit, select the point features. Let's say 1, 2, 3, 4, 5, 6. Let us give this a 7. Okay. So now we go for shortest path, layer to point, IIT lines, residential Powai. Endpoint is somewhere at CSRE library. Save it here. Yeah. So we click the run option, and now we see the shortest paths that are there. Just change the symbology here to say black color, having a width of 1. Click on apply. Okay, I think there's some issue with the QGIS when a lot of points are being considered. So let me just restart the software again. So like if we use the option, so basically what it would be doing that the shortest route from layer to point will give us the shortest path from each of the points of the source to the destination point. Like for example, if I click on this point, it would give me uh, one route from this point to the source. Then the second point, it will give a route from again the second point to the source. The third point will similarly give a route from third point to the source, fourth, fifth, sixth, and seventh. So each of the points in the point layer will give their own shortest route and associated cost function from the source to the destination. The reverse feature is also possible using the feature of shortest route from point to layer. From point to layer is where the source point is a single point and the destination points are multiple. Like this can be applicable to the cases when a person is living at a residential place and he selects some of the restaurants and he wants to find the restaurant that has the shortest distance. This is applicable for the case of shortest route between point to the layer. Then the next tool that we'll be studying is determination of service area. Service area represents like how much is the serviceable zone or I would say the buffer zone between a point that is centered around a point feature. So in this case, for example, if I select this point having a serviceable area of say 1 kilometer, then the serviceable area represents to these routes. So how to get results from this function? So we can go into it. So here we just create a new shapefile, serviceable area point, or say serviceable point. Geometry type, let us keep it as point. Click on OK. Start editing it. And if we go for some zone here, say adding one point at this junction. One point has been added with the ID 1. So we save the edits and stop editing. Next we go for the network analysis. In the network analysis, we would get the option of service area. Like there are different options: service area from layer and service area from point. Service area from layer means when there are multiple points in a feature layer. So in that case, the service area from layer would be applicable. And when there is only a single point, so in that case, service area from point would be applicable. So we select serviceable area from point. Vector representing the network is IIT lines. Path type to calculate is the shortest, that is the minimum distance. Start point is we go for the serviceable area point, which is this junction. Travel cost, distance for shortest and time for fastest. So here we can represent the distance in, say, in millimeters. So if we want a serviceable area of, say, 1 kilometer, we have to type 1000 here. And for advanced parameters, the default direction is both direction, and default speed is, we can keep it as it is, 50 kilometers per hour. So when we click on run, so it shows a serviceable area feature, serviceable area lines. We can go for its symbology and we change its color and line width. So here we see for the junction point at this location and having a serviceable area of 1 kilometer, the serviceable area that we see is the line that is highlighted in black color. So like the serviceable point is chosen in such a way so that it covers the most part of the any region, or like here we are considering the case of IIT campus. So if we keep the serviceable point at the center, so it covers most of the region in the campus. Serviceable area has its application in mostly the urban places. For example, the police stations or post offices, where they try to maximize the serviceable area that comes under each of these stations. So up to this part, has anyone any queries or questions? Please let me know. Any questions? Whatever has been discussed so far? Okay. So let us move to the next section. I hope my screen is visible to everyone. So, next part we move on is to the finding the closest destination. This case is applicable when there are multiple sources and multiple features. When there are multiple source points and multiple destination points. So we would be moving to this concept of OD cost matrix, which is the origin to destination cost matrix. In the previous section, we only discussed about when there is single source and either there is single source and multiple destination, or there is multiple source and single destination, or there is single source and single destination. But when it comes to multiple source points and multiple destination points, we come to the concept of origin to destination cost matrix. Each destination is mapped to the individual sources through the least cost value, and the resulting data are stored in the form of a matrix of dimension. The matrix has the dimension of number of sources by the number of destinations. So, like if here the number of column refer to the number of sources, say S1, S2, S3, S4, and number of destinations D1, D2, D3. Each column represents one destination. So this matrix should give the least cost value for each of this combination. When S1 is iterated over destination D1, D2, D3, D4. Similarly for S2, for S3, and for S4. So the data set and the procedure has been adopted from QGIS tutorials, and the data source is DC Open Data. So we can proceed with this for finding the origin to destination cost matrix. So for here, I'm removing the previous layers. So the first step is we have to install the QGIS Network Analysis Toolbox plugin. So here we just need to select, go to plugin, manage and install plugins. So we type QNIT 3, selecting QNIT 3, and we then click install plugin. So it would take hardly within a couple of seconds it's get installed. Okay, so this feature has been installed, this plugin. So the next step is we have to import the shape files that were available from the DC Open datasheet. So let me discuss what are the shape files that are available in the DC Open dataset. So here we have three dataset, three layer files. One is the roadway files, another is the address points, that is the source points, and the third is the adult mental health providers points, which is the destination points. So first we import the shapefiles for the roadways and the adult mental health service providers. Again, we start importing the shape files. We add the shapefile of address points. So it has a multiple number of points. It has a quite a large number of points. And also we add the shapefile of adult mental health providers. Okay, and also we need to add this feature of roadway block, which gives the complete road network. So roadway block can come in the middle. The first feature that we imported, the first two features are the adult mental health providers and the roadway block. Then we added the address points, and let us move this to the middle. We can change its symbology so that it becomes clearly visible. Say let us keep this as 0.25. And for mental health service providers, let us keep simple size 2. So if we look at the attribute table, we can see that there are 13 mental health service providers, and there are quite a lot of address points. Like each address point is referring to one residential address. So here our objective is from a selected address points, like if we select multiple address points and we want to see which of the adult mental health service provider is closest to that particular address point. So for this case, we have to first calculate the origin to destination cost matrix. So from these lot of points, we have to first extract, say, 1000 randomly selected points. So for that, we can search for random in the processing toolbox and go for vector selection tool and select random extract. So in random extract, the input layers is we would select as address points. The method of extraction, it is number of feature or percent of feature. Since we are interested in selecting only 1000 points, so we would go for the method as number of features, and the number of features that we would be selecting is 1000. And extracted random, like here we have to save it as a file. Here we go for OD matrix. Let us save the file as address 1000. So we select the run option, and this randomly chose 1000 selected points from the whole lot of address points. So we can uncheck this portion of address points, and now our analysis will be based on the source points and the destination points. The source point is address 1000, the source point layer, and the destination point layer is adult mental health providers. So here we can rename it as source point, the address 1000. For renaming, we just right click on this layer, rename layer, and we can just select origin points. For adult mental health providers, we just rename the layer and write it as destination points. So now we run the origin to destination cost matrix. For that, we go for this toolbox that we had recently installed, the QGIS Network Analysis QNet 3. We go for distance matrices. Then we select the option of OD matrix from layers as line in order to visually see the the shortest distance. So we select this option. So here our network layer is roadway block. From point layer, that means the source layer, the origin points. Unique point ID, let us keep it as say object ID. 2 point layer is the destination points. Unique point ID field is the same object ID. Optimization criterion is we would select it as shortest path, since here we have only the information regarding the distance. Here we need to select some direction field. Direction field has already been provided in the roadway block attribute table as summary of direction, the attribute summary direction. Value for forward by direction is say OP. Value for backward direction is IB. Outbound and inbound, it refers to these concepts. And values for both direction is VD. And we save this output OD matrix as a geopackage file, and then we click on the run option. So it would take some time for the analysis to be completed. Here the processing time is more since it is iteratively calculating the shortest distance for each of the source points to each of the destination points. So it has this cost function values associated with it, which are these numbers. Okay, the process will be running. So uh, till that time, like anyone has any queries regarding the discussions so far we have discussed, like starting from how to go for this optimization techniques, network analysis from point to point and layer to point that was discussed in the previous example. Anyone has any queries regarding the same? Okay, I think I can go by lesser number of points. So you can just cancel this here. Going for random extracts, address points, number of features. Suppose say only 20 points I'm selecting. So this is address 20. Then going for the option of distance matrices. OD matrix from layers is lines. Network layers is roadway block. From point layer is address 20. Unique ID is object ID. 2-point layer is destination points. Unique ID is object ID. Optimization criterion is shortest path. Entry cost calculation method ellipsoidal. Direction field is summary direction. Forward direction is outbound. Backward direction is inbound. Values for both direction is BD. Default speed we can set it as up to 50. And let us save this as a file. OD. This we can select the run option. Yeah. So for 20 selected points, we got the OD values as represented as line features. So like during implementation of OD, if we look at this attribute table of roadway block, So here it has this attribute of summary direction. Summary direction here, BD refers to two direction, both direction. IB refers to inbound direction and OB refers to outbound direction. So here the summary direction has been mentioned as a separate attribute feature, and for this we inserted these attributes, the directional attributes, in the advanced parameters. So here, if we see the source and the destination points, I can remove this layer. The source here is address 20 and the destination points is the destination points layers. So here we see each of the source point is connected to each of the destination points. The web-like feature that you are seeing is the cost function that is associated with it. So if I click on this table, open attribute table, it gives the total cost for each of the combinations of source and destination points. So if we just verify, so there were 20 source points, and let us check how many destination points were there. So there were 13 destination points. So when we look into this layer of OD matrix, so it gives a total of 260 points, which is the product of 13 and 20. So here the origin ID, that means the address ID, is connected to the destination ID, which is the uh, adult mental health service provider. So we see that after each origin ID has been connected to the destination ID, the origin ID is the changed, and the destination ID is also started from 1 to 13. So this is the similar thing that we were discussing about the OD matrix concept, where the number of rows represent the number of source points and the number of columns represent the number of destination points. So from this OD matrix, we have to determine for each of the source points, which destination point is the nearest. Like for each of this address point, which adult mental health service provider is nearest to it. So for that case, we just need to go for a server query toolbox. We go for this toolbox and we select SQL query. General. SQL query is there in the vector general processing toolbox. So here we go for the option of execute SQL. So in this execute SQL tool, we select the input as the OD20. We click on OK. Then SQL query, we select as select origin ID, destination ID, minimum total cost as shortest distance geometry. Then from input 1, group by origin ID. Here, okay. So origin ID, destination ID, these uh, features are there in the OD matrix, that is the OD20. And input 1 is the OD20, grouped by the origin ID. So we want to group the OD matrix through the feature of origin ID that has the minimum of the total cost, and the minimum of the total cost we would be representing it as the shortest distance. And so here the geometry field, you type it as geometry, and the geometric type as the line string, since the OD matrix represented the results as line string. So we click on the run button. Okay. Line string. Click on the run button. Yeah. So it gives us the SQL output. So this SQL output is giving us the result that for each of the address points, which mental health service provider is nearest to it. Like if we open this attribute table, so here for each of these 20 points, it will give the destination ID of the nearest health service provider and the corresponding shortest distance that is expressed in meters. So this covers the aspect of the origin to destination cost matrix and how to use the OD matrix to find the nearest destination place. So anyone has any query up to this section? Okay. So we can proceed to the next section of resource allocation. Allocation, as we discussed in the introductory section, is essential for some of the industries such as mining industry, metallurgical industry, or even chemical industries, where the optimization technique is used in order to find the least cost, whether it is associated in terms of distance or in terms of time. And depending on the least cost, the optimal amount of resource needs to be allocated to it. So here, integrated GIS and database management system enjoys the advantage of resource allocation from least cost optimization techniques, where daily production matters, like in the essential industries. The concept of resource allocation and logistics optimization has a key role to play. So we will be covering this third example as the mine to meal allocation. So for this, we are having a data set of a mine in which uh, there are mining sites and there are two milling units. Like there are 6 mining sites and 2 milling units. So the first phase would deal with the mine to mill allocation. So what meaning does it signifies is that for each of the mining site, what should be the meal that needs to be allocated for that corresponding mining site in order to minimize the distance or the time taken to travel from the mining site to the milling unit. So this is the map. The red dots, this represent the mining sites, and the green dots, they represent the milling units. So, like most of us will be thinking that the 2 milling units are quite near, and even though the mining sites are quite farther away from each other in terms of the distance, but the milling units are quite near. So, like one would be thinking that it is better to put all the the mining material or the ore into any of these milling units, but that is not the case because we have not introduced here the concept of routes. So if we add the concept of routes here, so here we see that each of the mining site has a different route and a different approach route to the milling unit. So like we have allocated each of the routes in terms of the route number, the length of the route expressed in kilometers, and what should be the speed limit for each of the routes that has been allocated in kilometers per hour. So here the concept of speed comes into existence because there can be some routes where driving at a faster speed may not be feasible due to some geotechnical constraints or due to some topological constraints or due to the condition of roads or due to other road network problems. So let us implement this exercise in QGIS. But we would be discussing first on finding the shortest route from each of the mining sites to the milling units M1 as well as M2. So for this exercise, we will be importing the files of mine 1 geopackage, mine phase 1, the point shape files, meal unit 1, the point shape files, and the routes 1 line shape files. So we can just assign some symbology for it. The roots are the black dotted lines. The mind phase, let us assign it as a star mark symbol. Two, prominent, let us make it three. And for the meal units, let us give a different color. And let us keep the mining area as yellow color. So for this exercise, since it is a continuous exercise of route optimization followed by mine to meal allocation and further like proceeded to the dumper truck allocation to each of the mining sites, we would be executing this exercise via Python programming. So for that, we would be opening this Python console. The symbol, this is the symbol for the Python console. We can close the processing toolbox, and from the Python console we can open a script. We'll open a new script. So here so here our first objective is how to find the shortest distance in terms of path length and in terms of time for each of the mining sites to each of the milling units M1 and M2. For this, we can do it on a case-to-case basis. So let us first start for each of the mining sites to the milling unit M1. So like this is the description. The mining sites are S1, S2, S3, S4, S5, and S6. And the milling units are M1 and M2. So let us proceed for route optimization for each of the mining sites to the milling unit M1. So for that, the first step is from QGIS core, import QGIS project. So this imports the necessary package files that are applicable for a QGIS project. And for numerical analysis, of course, you'd be importing the NumPy library, import NumPy as NP. The next step is to open the root layer file as a variable in Python. Let the name of the variable is say layer. So that is the function of QGIS project dot instance dot map layers by name. Since the roots layer file has already been opened in the QGIS layer console, so just typing it as roots would be sufficient. And we have to only open the first index of the root layer. Like that would enable us to open the root locations for each of these features in the root layer file. So for time to time, we can just execute the selected lines. The selected lines can be executed by using the option of Control and E. So the root layer file was imported as a variable named layer. And then we declare a data provider variable. Provider is equal to layer dot data provider. Okay. For the time being, let us delete this attribute of time. And using coding, we want to uh, add an attribute of time and calculate the time. Like from this attribute table, we can calculate the time as the length or the distance divided by the speed, where the length has been expressed in kilometers and the speed has been expressed in kilometers per hour. So here we use the data provided variable to add attributes of QGIS field, adding a QGIS field of time and mentioning the data type. The data type is uh, denoted by the representation of Q variant, not double. Double means it is a floating point of the double type. And applicable up to 3 decimal places. Here I need to put a square bracket. And then it is followed by layer dot update fields. So let us select these 3 lines and execute it. So here in the console, it gave us a value of true. When it is giving a value of true, this means that uh, a field has been updated in the roots layer. So if we again open the attribute table, we find that a field of time has been updated with each of the with each of the feature value as null, since we have not provided any time value for it. So we would be calculating the time as the ratio between the length and the speed, and we would be uh, providing this value, the ratio between length and speed, as the value of the time. So for that, again we go for layer is equal to QGS project dot instance dot app layers by name roots and the first index. In Python, the indexing starts from the zero, while in QGIS, the ID and the field ID, it starts from the number one. So we have to take this into consideration. So the index of time. So like we can see what is the uh, feature index of time. So it is sixth. The sixth column represents the time. So the time index is extracted as layer dot fields dot lookup field, like searching for the field of time. We execute these two lines. Okay. QGS vector layer object has no attribute field. Okay, it should be layer dot fields. Okay. So if we just write here as time IDX, so it is giving the index of 5. Index of 5 means in Python, since the indexing starts from 0, so the sixth column represents to the index of 5, and which is correct. The time index is uh, is having the index of 5 in Python. Now the next step is updating the time attribute for each of the features that is present in the roots layer. So for that, we iteratively calculate the value of time for I in range, length of layer. We declare a variable a is equal to layer dot get feature I plus 1. Since here the QGIS feature layer starts from 1 and the Python, the indexing starts from 0. So here we have to give the get feature starting from 1. So it should be when I is equal to 0, then the layer.get feature will be having the feature value of 1. So here it will be layer.get feature I plus 1 dot attribute. Here first attribute is the length divided by the same thing that corresponds to the time. Sorry, that corresponds to the speed. So we just copy and paste layer.get feature I plus 1 attribute speed. And if we want to express time in minutes, so we just multiply it as 60. Since the distance was represented in kilometers and speed was represented in kilometers per hour, the ratio of distance by speed will give us the value in hours. So in order to convert the time from hours to minutes, we have just multiplied 60. So we declare another temporary variable, ATTS, and create a dictionary of time which is assigned the value of A. Here this A represents to the value that we obtained from this line. Then feature is equal to layer dot get feature I plus 1, and for the data provider we update or change the time attribute values using the feature ID that we obtained from this line number 14. This is feature dot ID, and representing it as a dictionary of ATTS value. ATTS value is the value of A. So this case, the line number 15 updates the attribute values of time as the ratio of the distance and speed. So let us execute from line number 9 to line number 14. Okay. So when we hit enter in the console, okay, it is saying time is not defined. Okay, oh, sorry. Here I need to mention as time index, not time. So here I hit enter. So it is showing the value of true. So that means the value of time has been updated for each of the features. So if I open the attribute table for the roots layer, so I see the time values has been updated. So it is the ratio of length by speed multiplied by 60. So the time taken for to travel by route number 1 is 12.328 minutes. For route number 2, it is 4.344 minutes. For route 3, 3.899 minutes, and so on. So here the shortest route we have found both in terms of the distance as well as the time. In terms of time, it is represented as the fastest route. So now we want to find optimize the route for each of the mining sites for each of the meals. In terms of the shortest distance route, as well as for the fastest route. So, like for optimizing for meal M1, the first step is obtaining point coordinates for meal unit. Meal unit variable. So here again we go for layer and get the layer of meal unit. So it is QGS project dot instance dot app layers by name meal unit and index 0. We get the x and y coordinates as m1x for meal 1. The x coordinate is there dot get feature for the first feature, that is for the m1 meal 1 dot attribute x coordinate. So if we open the attribute table of the meal units, so it has for each of the meal unit, it has the x coordinate and the y coordinate recorded. So we are just extracting it as a variable of m1x, and similarly for m1y, we have the same thing just expressed as y coordinate. So if we just type m1x, it is showing the x coordinate, and m1y, it is showing the y coordinate. Now we want to find the shortest distance for each of the mine faces to the meal unit M1. For that, we go for processing dot run native shortest path layer to point. Shortest path layer to point. It is the same thing that we could be doing using the toolbar, but like for further analysis, we can write this as a coding, and we can use this. And it is having the parameters of input. For input, I am having the input file as roots. Okay, roots1 dot gpkg, and the layer name is roots. This is followed by strategy. The keyword strategy indicates whether you want to uh, extract in terms of the uh, time, that means the fastest path, or in terms of the distance, that is the minimum distance path. Strategy 1, it represents the fastest path. And for this example, we don't have direction fields. So we just leave it as blank. Value forward, that means the forward direction. There are no associated strings with it since it is a two-way direction. So for this case also we leave it as blank. Then value backward. This one also we leave it as blank. Then bidirectional value entered as value both. This also we leave it as blank. Then comes default direction. Default direction 2. It represents bidirectional route. And since here we are dealing with time, so we have to specify the speed field. Speed field in the routes layers attribute table, the speed field is having the attribute of speed. If we are giving the speed field attribute, so in that case we have to specify the default speed as 0. And topological tolerance, for that there is tolerance. We don't specify tolerance, so it is 0. Then the start point, start points is the line phase vector layer. So I'm just copying and pasting. Next comes the endpoint. Endpoint is, we have to express the endpoint in terms of a string. So it will be string of m1x concatenated by a comma, again concatenated by string of m1y, again concatenated by the reference system of the string of the points. So here we have the reference system as we can see the reference system here. It is EPSG 32643. EPSG colon 32643, and then the output is saved as a file. So I'm saving this as a file, for example. So let us implement this entire code. So this code is implemented. So the file name is S1 time. That means for the mine, uh, the mine sites to the meal unit one. We have mentioned the shortest route file as S1 time, the fastest route file as S1 time. So we open this fastest route file for meal S1 by QGS project instance. So let us check. Okay, so here just need to select refresh. Okay, here after processing the S1 time got saved, we just click on here and open the attribute table. So here we can see for each of the phase mine phase, that is mining sites A, B, C, D, E, F, or S1, S2, S3, S4, S5, S6. We have their corresponding X coordinate, Y coordinates, and the start and the end. For each of the end coordinates, the coordinates represent the milling units, and the cost has been represented as time in hours. So here we open this S1 time as a layer variable, and then we want to store each of the cost function variable in another Python based variable. For that we write for field in layer dot fields print field name, field dot name. So here it will print what are the names of the fields. If I hit here enter, so it has the FID, mine phase, X coordinate, Y coordinate, start, that means the start coordinate, end means the end coordinate, and the cost function value. And then we proceed of storing the cost function values as separate Python variables. Here we declare the Python variable name as also S1t. S1t is equal to numpy dot zeros having a length of layer. Here, each of the layer file is listed as a field, is listed as a list field. So here we put length of layer, and having a data type of say float 32. And then we iteratively extract and store the values of the cost function in S1t. So for that, for I in range length of layer, value is assigned as layer dot get feature I plus 1. There is this uh, QGIS layer.get feature. So here, that's why we have put again I plus 1 dot attribute of cost. So for display purposes, we are just printing the values, print value, and S1T of the ith index is assigned as the value. So let us execute this code. So here it prints the cost function values, and it also assigns the values as S1T. So if I just type S1T, it gives me an array of data type float 32. Similarly, we would be doing the same thing for uh, minimizing the route with respect to the distance for each of the mining site to the milling unit M1. In the previous case, we did it for the fastest route. Now we will be dealing for the shortest route. So here, if we look the S1 time, change the routes. Okay. So the S1 time routes are represented as the black solid lines for each of the mining sites. So how the routes have been designed as to approach the milling unit M1. This has been done with respect to minimization of the time, that is the fastest route. So if we want to do the same for uh, the shortest route, that means the minimum distance route, so we have to just simply copy and paste this thing, and we have to modify certain values. So it's been mentioning M1 distance optimization. So here for the processing run, we have to go for okay, routes 1. Here the strategy is 0. Like for the shortest route, the strategy was 1, and for the the fastest route, the strategy was 1, and for the shortest route, the strategy is 0. And here the output is we have to set it as S1 distance dot geopackage file. So if we click here and execute it, it gets saved as S1 distance, and we double click to open this S1 distance file, and then we execute. Remaining all the lines is the same, except that we declare here S1 distance, and instead of S1T, we create a new variable S1D, and then we uh, store the cost function values in the S1D variable. So let us execute this line. So here the cost function values are expressed in terms of the distance. Now, if we make a comparison of S1 time and S1 distance for each of the mine sites to the milling unit, so this is the representation of the shortest route. This is the representation of shortest route, and this is the representation of the fastest route. So here we see that there are some differences in the especially at this location. The shortest route for S1 to Millings unit M1 was something a straight line. But when it comes to a fastest route from S1 to M1, the fastest route is something going via route 1 and then taking a diversion to route 5 followed by route 3 and then route 9 followed by route 6. This reaches to the mailing unit M1. And if are there any other changes? No. I think this was the difference between the shortest and fastest routes for uh, the mine sites to the milling unit. So similarly, we can do the same analysis for all the mine sites to the milling unit M2. For that, we just copy the previous portions and we need to change the values. We have to open the mill unit again and we have to extract the code X and Y coordinates for the milling unit M2. So M2X and M2Y. So let us see M2X and M2Y. And then we go for the processing for the fastest route. So it created a file of S2 time. Then we store the values of the cost function for the fastest route for the milling unit M2 as the variable S2T. So it gives us the cost function, that is time expressed in hours. So we can implement the same thing in terms of the shortest distance. Here the strategy is again 0. So it created a file of S2 distance. And then we extracted the cost function values and stored in a Python variable of S2T. So for this case, optimizing the distance for each of the mine sites to the milling unit M2, we again make a comparison between the shortest and the fastest route. We are able to observe one difference in this path. The shortest route for the mine site S5 to M2 goes along this, but the fastest route from the mine site S5 to M2 is this. The shortest route is along this direction, the right hand side direction. So comparing both of the cases for all the mine sites to each of the milling units M1 and M2, we observe that the speed factor for each of the haulage route is affecting the route assignment from which the dumper trucks can go from the mine sites to the milling units. Now, again, if we make a further comparison, in order to allocate for which of the mine site, which milling unit would be most suitable, so we make a comparison of the cost values expressed in terms of the shortest route and expressed in terms of the fastest route. For shortest route, these were the function values obtained for milling units M1 and M2 with respect to the mining sites S1, S2, S3, S4, S5, S6. And for the fastest route, these were the cost function values obtained. So if we only consider the fastest route in order to maximize the mineral production, so instead of going for a shortest route approach, we have to go for a fastest route approach. And so by comparing the values for each of the mining sites and the time taken to reach the milling units, so here we can make a determination of which milling unit is suitable for each of these sites. So for that, we further extend our coding. We declare an empty list as meal allocation and iteratively select the meal for each of the mining site for I in range S1 time, since we are only dealing with the fastest route for this case. So we provide an if then condition, if else condition, if S1 time of ith index is lesser than S2 time of ith index, then meal allocation dot append meal one. Like if the time taken from the site to the meal one is lesser than the time taken from the site to the meal two, then the dumper truck has to go to the meal one. Else, meal allocation dot append M2. So let us see what does the meal allocation variable issue in. Yeah. So for this case, since each of the distance had the fastest route towards the meal M2, so all each of these mining sites have been allocated to the meal M2 rather than the meal M1. So the mining site S1 has to take a diversion along this route and approach towards the mill 2, and similarly the other mining sites have also take the diversion routes and approach towards the mill 2. The last aspect that we will be covering is dumper allocation to each of the mining site. So for that, it is a simple linear optimization problem. Suppose the mine has 30 dumper trucks. So how many trucks should be allocated for each mining site? So it is a programming problem of say 6 variables. So if x1 to x6 represents the number of trucks allocated for say s1 to s6, and the number of dumper trucks each mining site can handle at one instance is each of the sites can handle one dumper at one instance. So when one dumper will be going to the site, the other dumper should be returning back from the mining site. And there has to be some additional constraints like each of the mining sites S1, S2 combined should have a balanced number of trucks. For S3 and S4, it should have a balanced number of trucks. And for S5 to S6, it should have a balanced number of trucks. And few other constraints that would be mostly applicable to the linear programming problem. So this is how the solution is obtained. Okay, I think here I need to make some editing. Here S4, let us make it as 2 trucks it can handle in at one instance. Similarly for S5 and S6. So here the objective function is maximization of um, one is at one instance it can handle only one truck, and x1 here represents the number of trucks, and t1 here is the time taken for both the onwards and the return journey. So from the cost function that was estimated, we simply multiply by 2 in order to obtain these variables t1, t2, t3, t4, t5, t6. So for second mining site also, the number of trucks it can handle at one instance is 1. For third mining site, it can handle 1 truck. And for fourth, fifth, and sixth mining site, it can handle up to 2 trucks. So this is the objective function that needs to be maximized and subjected to the constraints that the sum of each of these x variables should be equal to 30. Each of these x variables should be greater than equal to 0, and the additional constraints that were put forward in the problem. So using this, an optimal solution is obtained. So we can quickly write the coding for this. So we have to multiply the time by twice. SP is the optimized time for each of the mining site to the meal. Okay. So here we declare an empty variable st having the shape of s1t. So st for each index is the minimum between the S1T and the S2T. And then it is followed by multiplying the minimum time twice for the inbound and return journey. For linear programming problem, we import the function of linear programming from scipy, scipy.optimize, import linear programming. And then the Python handles the linear programming not as a maximization function, but as a strict minimization function. For that, if this is the maximization function, then we have to mention it as a minimization function. This would correspond to -1 x1 t1, -1 x2 t2, -x3 t3, -2 x4 t4, -2 x5 t5, and -2 x6 t6. Similarly, the constraints will also be the negative constraints. So this would correspond to -x1 -x2 should be less than equal to -8. This one -x1 should be less than equal to -3. -x3 should be less than equal to -4. This would be, since x3 plus x4 is less than equal to 12, so it would be as it is. So this is x3 plus x4 is less than equal to 12. This would be again -x2 minus x3 is less than equal to -10, and this is -x5 is less than equal to -3. So the similar values we have to put it as coefficients in objective function. The objective function is a list of values. -1 into t1. T1 is the STT variable indexed at 0. Similarly, for the second variable indexed at 1, then indexed at 2, 3, 4, and 5. The inequality constraints, these are the inequality constraints. These are the inequality constraints. And this is the equality constraint. And the bound for each of the variable should be x1 element of 0 to 30. Similarly for x1 to up to x6. So we write as the LHS inequality in as an array form. The right hand side of the inequality in as array form. The equality constraint, the coefficients is array form. Here x1, x2, x3, x4, x5, s6. So all the coefficients are equal to 1. And RHS equality again as a value, that is 30. And then we have the bounding conditions of 0 to 30 for each of the variables that needs to be estimated. Now we optimized using the optimizer option, linear programming with C as the objective function. A unbounded is equal to LHS inequality. E unbounded is equal to RHS inequality. A equality is equal to LHS equality. E equality is equal to RHS equality. Bounds variable B and D, and method is, let us consider, revised simplex. There are a lot of other methods that are available for linear programming based optimization. So if we run this, yeah. So the optimizer got run, and when we enter the value of OPT, it assigns the number of dumpers that will be allocated to each of the mining sites. For the site 1, there has to be 3 dumper, for site 2, 6 dumper, for site 3, 4 dumper, for site 4, 14 dumpers, for site 5, 3, and for site 6, it has assigned the value of 0 dumper. So the key takeaways from this presentation are: the application of GIS in supply chain management would help in optimization of transport and faster delivery, and would minimize the costs and increasing the end user satisfaction. And route optimization will prevent unnecessary delays in transport and logistics, and with overcoming of supply shortages, and with the use of GPS and GNSS, monitoring of transportation is possible, such as the use of vehicle routing or the truck dispatch system. So these are some of the suggested readings, like how the GIS has been used extensively in supply chain management, in mining and construction activities, and how GIS acts as a decision support for